So in this lecture, we will discuss about the clipper, clampers and voltage doubler. Okay, so let's start discussing the clipper circuits. So the clippers are also sometimes called as limiters. Okay, so as the name suggests, the clippers means it's clip the signal. So let's try to understand what is a clipper. Suppose this is my clipper block, this is my V in and this is my V out. Okay, so this is my clipper, and the characteristics will be something like this. If this is a sine wave that I am applying as V in, so this is the input V in, the black one. The output will be the clip version of this one. Okay, so if I consider this as a zero crossing, okay, so it can clip at maybe at V plus voltage and V minus voltage. Okay, this is of course the zero. Okay, so this is the characteristics of the clipper circuit. And of course, if I try to draw the if I try to draw the input output characteristics, it is going to look like something like this. So this is my VIN and this is my V out. So the characteristics of the clipper is something like this. So when the input is higher than higher than 0, larger than 0, it's going to clip at the point where this is V plus, and of course my output also will be constant, right? If my input is more than V plus, the output is going to become constant. It's going to get clipped. Okay, it's going to stuck at V plus. Whereas if my input is lower than V minus, okay, so again it's going to get stuck at the V minus. So this is the basic characteristics of a clipper. So let's try to see how we can achieve this kind of clipper circuit using a diode. So first we'll start discussing this upper clipper. So let's see what is an upper clipper. So this is my V out, this is my V in, and of course we can connect ground here. With respect to ground, I can say, okay, this is my ground. So if you see here, I'm connecting this diode through a resistance. Okay, so now if my V in is less than 0, this diode is going to become off. It's going to become in the off condition, right? So so if I try to plot the V out by V in, so this is my V in, this is my V out. Okay, so what it means is if V in is lesser than 0, so of course V in is equal to V out, because this diode is always in off condition. The other thing which I have forgot to mention in the previous slide is here the slope is equal to 1. Okay, the slope of this line is equal to 1, because when my V in is in between V plus and V minus, my V out is going to follow my V in. So you can see here, right? The V out, this red color V out, is perfectly following my V in, okay, when it is in between V plus and V minus. Okay, similarly in this case also the slope is 1, okay? Slope is 1. And if you see, when this is lesser than 0, this is off condition. And if you consider the diodes starts turning on at 0.7 volt, that means till my V in is 0.7, okay, 0.7, my diode is going to be in off condition and V out is equal to V in. But as soon as it reaches 0.7, we know that we have to replace this diode with the constant drop model, okay, we have to 0.7. Okay, so my V in may increase. My V in may increase and it can become large, but you can see that my V out will be constant and it will be only it will be fixed at 0.7, whatever the value of my input voltage may be. Okay, so basically what is happening here is there will be a potential drop between V in and V out, but whereas this V out will be constant. Of course, the current through the diode will increase, but the potential difference across this diode is going to become constant at 0.7. So this kind of is called upper clipper because it is clipping the upper half of the V in. Okay, so we can get the lower clipper as well. But if you try to see the if you try to plot the transient response, right? So if this is my V in, okay, this is my V in, my V out is going to look something like this. It's going to clip at 0.7, and for voltage lesser than 0.7, this is the my V out. Okay, so my V out is going to follow V in, but if it is above 0.7, it's going to get clipped. So this is upper clipper. Similarly, we can get a lower clipper by just reversing this diode. Okay, in case of the lower clipper, the direction of the diode will just get reversed. Okay, so basically what is happening is if this is at 0.7, then only it will start conducting. Okay, minus 0.7, and the whole thing gets clipped. Okay, so characteristic equation is going to look like something like this. So till minus 0.7 is minus 0.7 minus 0.7. So my V out is equal to become V in, but after minus 0.7 it's going to get clipped. So this kind of clipper is called lower clipper. Now if I combine the upper clipper and the lower clipper, I'm going to get combined lower and upper clipper. So this was my upper clipper, and if I add one more diode here, so this is going to act as the lower clipper. Okay, so basically this is what is going to happen. Okay, so when it is more than higher than 0.7, right, this diode is going to turn on and it's going to get clipped after that. Okay, again this is at 0.7 plus 0.7. Okay, and as soon as this voltage become lower than 0.7 minus 0.7, again this diode is going to turn on and I'm going to get a clip at minus 0.7. Okay, this is at minus 0.7 and this is at minus 0.7. Okay, so this is how the waveform is looking like. It will get clipped at 0.7 and it will get clipped at after minus 0.7 as well. Okay, okay, so now it's fine. So we have clipped whether it's upper or lower, we have clipped it at 0.7. But the question comes is what if I want to clip at some other voltage other than 0.7? Okay, maybe I want to clip at 1 volt, 2 volt or 2.3 volt, something like that. So what should we do? Okay, so let's try to understand upper clipper with offset. Okay, I don't want to clip at 0.7, rather I want to clip at some other voltage. So this leads to the upper clipper with offset. Okay, so this was my upper clipper without offset. Okay, it was just clipping at 0.7, but as I was mentioning, okay, I want to clip at a voltage, maybe let's consider some value, maybe I want to clip at 2 volt. Okay, I want to get clip, I want to have some this kind of characteristics where I want to get it clip at only 2 volt. Okay, 2 volt here, and here it is also 2 volt. Okay, So basically what it means, if you see the principle here, so when it is at 2 volt, this diode should be on, okay? So this diode should be on only when it is at 2 volt. That means, and we know that the drop across this diode is 0.7. That means this potential should not be 0. This should be 2 minus 0.7. That means this should be at, 1.3 volt. Okay. So which means I need to add a series voltage source to get this 1.3 volt at this point. So what it means is I need to add a voltage source. Okay. Which is at, in this case, let's call it as VB, voltage source VB, equal to, in this case it is 1.3 volt, okay? And we know that voltage drop across this diode will be 0.7. So ultimately, when it will be at 2 volt, okay, then only it will start clipping. So okay, so by varying this voltage VB, we can clip at any value, okay? So this is how we can get an upper clipper with offset, okay? And similarly, I can get this lower clipper with offset, and so what I need to do is that I just need to reverse the battery, okay? And I can get an upper and lower clipper with offset by the combination of these two. So let's try to see how to design a combined upper and lower clipper with offset. Okay, so maybe let's start with this upper clipper. So I just need to add a lower clipper here, okay? So maybe let's consider that the lower clipper is clipping at maybe at minus 3 volt. So for that, of course I need to reverse the direction of the diode, okay? To get my lower clipper, okay? And now we want, of course, the slope is 1, and we want it to get clipped at minus 3, okay? At minus 3 volt, okay? Of course the slope is 1 always. So what it means is that when this reaches minus 3 volt, this diode should be turned on. That means this potential will be definitely zero point 0.7 higher, right? So 0.7 higher means, which means that this should be at minus 2.3 volt, okay? That means, and of course this is the ground, okay? So that means I should connect a reverse battery, right? So my VB2 will be in the reverse direction. So this is my VB1, and VB2 will be in the reverse direction because this is zero potential. So I need to connect this battery in this reverse polarity so that my this point, the VB2, right? VB2 should be something like this. So my VB2 will be 2.3 volt. That's why the potential at this node will be minus 2.3 volt. And that's how I will get a clipping at minus 3 volt. Okay. So this is the combined upper and lower clipper with offset. Okay. Now let's try to analyze the clamper circuits. So clamper circuits are those circuits which are used to adjust the DC value of a waveform. Okay. So if the clamper circuit don't distort the waveform, you see the clipper circuits were distorting the waveform, they're clipping the waveform. Whereas the clamper circuit don't distort the waveform, rather it's either adds the DC or it can be used to subtract the DC value. So let's try to understand, okay? So this is my V in that I'm applying to this clamper circuit. So this is my clamper circuit. So this is my applied voltage V in. Okay, this is with respect to the time, definitely. So and let it be, this is going maybe from plus 4 volt to minus 6 volt. Okay, and this is my clamper circuit. The clamper circuit is basically, it has a capacitor. Okay, capacitor, and we have this diode which is in this direction. Okay, so this is my V out, it's positive and negative. Here I want to analyze how does my V out changes with change in V in. Okay, so let's try to analyze what happens to the V out. Okay, so now it has started initially with minus 6 volt. Okay, so in this case we will assume that this diode is ideal. Okay, so we'll try to analyze this one with this VD on is 0. Okay, so basically what it means is that if in my diode characteristics, okay, so as soon as it is positive the diode will be on, right? So currently we are considering the diode characteristics to be on only after 0.7, but what we'll consider is that, so it is on as soon as the diode is little positive. Okay, so this will help us to understand the clamper circuit easily. So now what will happen is, suppose this is at suppose this is at minus 6 volt, and initially the capacitor was not charged, so this is at minus 6 volt. Okay, and of course because this is at minus 6 volt and capacitor was not having charge initially, so the voltage drop across this capacitor will become 0, right? Because we know the formula of the capacitance, right? If the charge stored is 0, then the potential we know that the so we know that Q equal to CV. If my Q is 0, V is also going to become 0. Okay. So now what will happen? This diode will become on. So this will be at minus 6 volt, and the diode will become on, and this will start charging the this capacitor, and eventually this will reach to a voltage 0, because we know that the diode drop is 0. Okay. So now it will store discharge, right? This is plus and minus, the VC will be 6 volt. Okay, so this will be at higher potential, this will be at lower potential, and the potential difference across this capacitor is 0 minus of minus 6, it is 6 volt. Okay, so now in the other half, when it is at plus 4 volt, okay, so it is at plus 4 volt, what is happening is, you can see here this the charge stored in the capacitor is and the potential difference across this capacitor is 6 volt because of the charge stored in it, and this is plus 4 and this is plus 6, so the potential at this node will be 4 plus 6, 10 volt. Okay, so it's going to become 10 volt. So when it is at plus 4, it's going to become 10 volt. Okay, and again when it's going to go at minus 6, it's going to become, again the same thing is going to become, it will be at minus 6, and this will be in on condition trying to charge this capacitor, so it will be at 0 volt. Okay, so and the potential difference that is developed across this capacitor will be again 6 volt, and the charge will be stored. Okay, so finally this is what it's going to look like. This is my 0 volt. So this is my 10 volt. Okay, so if you see here, if you notice here, there is no change in the type of the waveform. Only thing is that it just got shifted. Okay, so even if you see here, the peak to peak voltage is plus 4 minus or minus 6, the difference is 10 volt, and here also you can see that 10 volt. Only thing is that the DC value has been shifted. This kind of circuit is called the clamper circuit. Again, depending upon how we are putting this diode and putting a potential difference here, we can also get different kinds of variation of the clamper circuit. And of course, if I reverse this diode, then I will have opposite kind of characteristics. So let's reverse the diode here. So now let's try to again analyze this one. So now in this case, what will happen is, of course, when it is at minus 6 volt, okay, of course this is a negative, so the diode will not be on, okay. But whereas when it is at plus 4 volt now, this diode will become on and it will be conducting in this direction and it will be charging this capacitor, okay. So it will charge this capacitor and then it will become, plus we see it will charge, it will become 0 here, right. So and this will become plus and minus, it will become 4 volt, okay. So the capacitor, this will be at positive plate and this will be at negative, okay. So it will be this will be plus 4, this positive and negative, okay. Now in the next time when it is at minus 6 volt, okay. So this is at minus 6 volt, okay, and I'm having a battery in series, which is, this side it is positive, this side it is negative. So here what I'll get is I'll get minus 10 volt. So it is something like this. I have a minus 6 here, 6 volt here, and I'm having a battery here which is 4 volt, okay. So basically it means I'm going to a lower potential here, right. So this should be minus 10 volt, okay. So yeah, so this is what it means. So when it is at minus 6, it will become minus 10. And again when it becomes at 4, it will become at 0. So in this case it is minus 10. And when it becomes at plus 4, right, again this diode is going to become on, right, and it will become 0. And when again it is going to become, and it will store this store the charge here, and the potential difference across this capacitor is going to become plus 4 volt. And you can see here at minus 6, again it's going to become minus 10. So it's going to become minus 10 when it is minus 6 volt, and it's going to become 0 when it is getting 4 volt. Okay. Okay, so this is 0. Okay, so you can see here this inverse effect. Okay, so it was shifting towards in the upper direction. Now it is has shifted in the lower direction if I just reverse this polarity of this diode. Okay. Okay, and just like in the clipper circuit, we can add a battery here and we can do the offset. Okay, we can add, we can decide where we exactly want to shift this waveform. Okay, so by using a voltage source in series with this diode. So let's try to analyze that as well. So now let's apply a potential here, okay, PB, and let's see what happens, BB, okay. Okay, so now, so now as we know that when only this is negative, then only this will be on, okay. So when it is at minus 6 volt, when it is at minus 6 volt, okay, so then this diode will be on, and we can see here that there is a BB drop, okay. So this is the drop across this diode is 0. So here the potential will be PV, okay, plus BB, okay, because the diode drop is 0, and of course here we are assuming that this, because this diode drop is 0, so it will be BB. So now if you see the potential difference across this capacitor is basically, so this is at positive side and this is at negative side, and it is VB minus of minus 6, okay. So the VC that is stored is VB minus of minus 6 is basically, I can say that it is VB plus 6, okay. So VB plus 6 volt will be stored across these capacitor. So this is at positive side and this is at negative side. You can see that the potential difference is much higher compared to when this VB was 0. Okay, so VB plus 6 has been is the potential difference that is stored in this capacitor. Now when this is at plus 4, okay, so you can see here it will the potential here, it will be, the diode will be off now because it is at higher potential, and here it will be basically, you can see here right now I have a 4 volt here, and in series, right, this is positive plate, this negative plate, so and I have VV plus 6, so here basically it means that VV plus 6 plus 4, basically VB plus 10. Okay, so when it is at 4 volt, it is going to become VB plus 10. Okay, and when it is at minus 6 volt, of course this is at just VB. Okay, and the surge stored here is such that the potential difference is BB minus or minus 6, so BB plus 6. Okay, so it's going to become BB at this point. Okay, only BB. Okay, okay, only BB is here, and of course we can, it will continue something like this. Okay, so if you note that the whole waveform is shifted by this amount VB. Okay, so still the peak to peak voltage, is still 10 volt. See here it is 10 volt, so it is also still 10 volt, but only the whole waveform has been shifted by VB. And of course, depending upon how I orient the diode and this potential, I can get different kind of shift. Okay. So the last thing which I would like to conclude is that note that we have not connected any load resistance across this clamper. Okay, we have not connected RL. So if you are connecting this RL, we have to make sure that this RL and C is much higher than the time period. Okay, or basically the time constant, RC time constant should be much higher than the time period, because we don't want the charge of this capacitor to discharge very fast. Okay, even if it is discharging, it should be very slow. So otherwise in one phase we are storing the charge, and in the next phase when this diode is off, we don't want the capacitor to discharge very fast. If it is discharging very minorly, it's fine. So the clampers are useful for only those kind of circuits where my load impedance is very high. Okay, so it is not useful for those circuits where my load is very small. Okay, so now we'll discuss this voltage doubler circuit. So what is this circuit? So this is basically a circuit if my input is a sine wave with an amplitude of BP, then my output will be a DC voltage with an amplitude of twice BP. That's why it's called voltage doubler. So let's see its circuit. Okay, so this is the circuit of the voltage doubler. I have two capacitors, this one C1 and C2, and I have two diodes D1 and D2. Okay, and my output is observed here, V out. This is positive and this is negative. Okay, and my V in is here. Okay. Okay, so now what we'll do is basically we will apply a sine wave here, which has a peak amplitude of BP, something like this. Okay, BP, and we have minus BP. Okay, so what I'll expect is that this output will be 2 BP. Okay, 2 BP with a plain DC voltage, double than this peak amplitude. Okay, so how does it happens is, so suppose when this is at minus BP, so this quite follow the principle of the clamper circuit. Okay, so suppose this is at minus BP, and imagine there is a diode drop, and imagine this is also an ideal diode. Okay, ideal diode, that means this is on and this will be at 0 volt, and this will be basically at a higher potential compared to this one. So the charge stored here in the VC1 will be equal to BP. Okay, the potential difference across this C1 will be BP for the charge that is stored through this diode D1. Okay, so this will happen during this cycle. Okay, especially when you reach at minus BP. Okay, so now as soon as it becomes more than BP minus BP, okay, this diode will stop conducting, because if you see here now, what will happen is, if it is a little more, right, it is little more than minus BP, maybe let's minus BP by 2. Okay, so this is at minus BP by 2, and I am having this battery, or this, I can treat this capacitor like a battery, right, with a potential drop of BP. So here it will be what? It will be it will be, so basically this is at it is something like this. I have a battery which is BP, and this is minus BP by 2. So here it will be BP by 2, because this minus this. Okay, so yeah, so that means this diode will be in off condition. Okay, so this diode will be off condition, and now this will be in forward bias condition, and it will keep charging this one, and it will be on till the point this reaches BP. Okay, this point reaches BP. So basically it will reach till this one. Okay, so it will till reach this one BP. So when it will reach this BP, so this BP plus this VC1, so BP plus VC1, it will be twice BP. Okay, this will be at 2 BP, and assuming that the diode drop is almost 0, so this will be also at 2 BP, and this will now charge this capacitor C2. Okay, so this will charge this capacitor C2, and it will store this one. So during this phase, this capacitor is charged, and during this phase, we are charging this capacitor. Okay, so it is basically, we are treating this capacitor like a battery. Okay, and we are using this source and this one in series, and I am able to get 2 BP. And we can also design some kind of circuit. You see, we are just using this, charging this capacitor, and we are putting them in series. So we can also make some arrangement such that instead of 2 BP, we can make it 3 BP. So of course, we are not going to discuss those kinds of circuit in this course, but it is possible. Okay, so, and of course here with the condition again here is, this circuit cannot drive a large load. Okay, because we know that if I am having a very RL, large load in the sense that which has high IL current, that means this resistance should be small, then this is going to discharge this capacitor C2 when this is in the off condition, especially. Okay, so when this is charging, this is going to discharge. So if you see here, if this resistance is large, we are going to see some kind of ripples, because it's going to discharge when this is charging. So if I am connecting this load resistance RL, I have to make sure that this RL is large. Okay, that's why even though it is acting like a rectifier and giving a twice BP output, right, this giving a plain DC twice BP output, because I am not able to drive large load, right, so I cannot use voltage doubler in place of my half wave rectifier or full wave rectifier. Okay, so with this we'll end our discussion on the clippers, clampers, and voltage doubler. I suggest that you can construct this circuit in the LT Spice and see yourself that this is working as a voltage doubler. Okay, thank you then.